Hello students, my name is Shashank Shekhar. So in the previous class, we have seen the preparation of hydrocarbon. In today's class, our focus will be conformation. Okay, so let me clear this thing. So when you consider alkane, then okay, we have prepared it, right? We are good to go with preparation. Now the second part comes, what is the reactivity? What is the structure of the ethane or any other alkane? So we get to know about that, right? So I'm trying to say that the thing is about now structure. So what is the structure? How is this alkane molecule placed? What is the stable weight the atoms should be placed so that the system has a minimized energy? Okay. So for that we will learn about conformations. Okay, we will see conformations of ethane. Then we will try to represent the conformation with two types of projections, which are namely Sohor's and Newman. And with the help of this projections, we will try to see the relative stability of the conformation. At last, we will differ between conformation and configuration. So two thoughts are there. One is conformation, second is configuration. So let us start our lecture. First of all, well, let us talk about conformation. So when you see alkane, it has carbon-carbon single bond. So that thing is clear. Alkane has carbon-carbon single bond. Now, what happens? The electron distribution around the bond. So if I talk about this bond, so electron distribution along this bond is almost symmetrical. We know it. They are very polar, non-polar in nature. So there is no polarity in the bond, and all electrons are symmetrically distributed, with approximately symmetrically distributed. Now, this allows a very this allows a free rotation of the carbon-carbon single bond, right? So means you think it in this way, that there is a rod. Okay, there is a rod. On the either side, you have two wheels. Okay, two wheels attached to that rod. Now you can rotate both of this wheel independently. Now this rotation that I'm talking about, that results in a different spatial arrangements of the atom. Because I am saying that wheel. Okay, we are taking the example of wheel. So wheel is symmetrical, so you rotate it in the either way, that will give you the same thing. But suppose in place of wheel, we take something that is unsymmetrical in nature. Now, two unsymmetrical things have a configuration, relative configuration, which will be different from one another and different in terms of energies also. Because since now the interaction is different, now if two atoms are placed close to each other, then the electron-electron pair will repel more. If they are placed apart from each other, then the repulsion will be decreased. So in this way, many other interactions are present, and that results in kind of, I can say that, different energies of the same atom, same molecule, but different conformations. Okay, and this is only possible for the case of alkane because there is single bond that is present, which allows the free rotation of the carbon-carbon on the either side. Now, why can't we do it with a double bond? What is the difficulty with the double bond? So when there is the double bond between carbon, what happens is that you can't rotate it. Okay, so you can think it of in a way that if you just connected the similar wheels which you've connected earlier with the help of one rod, you connect it with the two rods. Now, if you try to rotate it in this case, then it would result in the breaking of bond. So you have to first break the double bond, and then only the rotation will be allowed. So this rotation, this free rotation, is only um, applicable to the carbon-carbon single bond. Clear? And the rotation results in different conformations which are having different energies. Now, this spatial arrangement, due to different position of atoms around us, rotation of bond, rotation of carbon-carbon single bond, is called as conformations. Okay, so you will, of course, you will get different type of structures because of the rotation, and those structures or those different structures in terms of their spatial arrangement are called as conformations or conformers or rotamers, because upon rotation we got those things, so they are also termed as rotamers. Now this number of rotamers, if I talk about the number of rotamers, then there are infinite possibilities. Okay, there are infinite possibilities of conformation. So you can just think of it that if two wheels are rotating, okay, then suppose each part of wheel, so I'm taking that each coordinate of wheel is unique, then that would result in a number of configuration or number of, sorry, not configuration, number of conformations, okay, because the relative stability can be in varied form. Okay, clear? Now consider a ball and a stick model of ethane. So what are we taking? Ball and a stick model. Okay, so bonds are representing, stick are representing the ball bonds, and balls are representing the atoms. Now if you keep one atom stationary and rotate the other carbon around the CC axis, then the rotation would result in an infinite number of spatial arrangements. Okay, you take it in this way. Here is one carbon, take another carbon, you connect them with a ball, you take two balls instead of atoms, and with each atom connect three hydrogen atoms and one stick in between these two. Now you keep one of the atoms fixed and try to rotate the other, then you will see that number of relative arrangements are possible. So with respect to this, it can be here, 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 and that would result in infinite number of configuration. Okay, now these are called conformational isomers or conformants, means the various various conformations I am talking about, they are called as conformational isomers, and there are infinite number of conformational isomers that are possible. Now during this rotation, so if I talk about during this rotation, there is an interaction. Okay, see, there are two types of interaction. A student gets confused in that. So one is steric strain, another is torsional strain. Now there is a difference between both of these two. Okay, they said what is the difference? So if you talk about the steric strain, so suppose this is your carbon, okay, this is your carbon, and these are hydrogens that are attached to this carbon. Now two hydrogen will repel each other because of the electron density that are surrounding this hydrogen. Now if I talk about the torsional strain, suppose this is a bond, okay, this represents the bond. Here is the carbon atom, okay, sorry, here is a hydrogen atom, and here is a carbon atom. In between there is electron density. Similarly, in between there is electron density. So when we place two electron densities parallel to each other, such that if we view it from the left hand side, then there is then this side is not visible, then that would result in electronic repulsion between the bonded electrons. So what I mean here is that the steric strain is due to the repulsion between the electrons that are present on the atom, whereas torsional strain is due to the electron that are present in the bonds. Clear? So this is the difference between them. You should be aware about it. Now, one such conformation in which hydrogen atom are attached to two carbon are closely related is called eclipse conformation. Now, out of the infinite number of conformations that are possible, we will take two to maximum three types of conformations. One would be eclipsed, another would be staggered, and third one be skew eclipsed. Okay, so we'll not talk about skew one. Skew. So yeah, here it is written. So another intermediate conformation is skew conformation. So any conformation that is not eclipsed or not staggered, they are called as skew conformations. Now it may be remembered that all the conformation bond angle and bond length remain same, right? Bond angle and bond length will not change. So this is very, very important. Okay, so this should be remembered always. So when you talk about different conformations, okay, of a conformer, sorry, different conformers of a conformation, then you will see that each of this conformer are having the same bond length, and in addition to that, they have the same bond angle. Okay, so you don't do that. Okay, it is having more repulsion, so it will change its bond angle to adopt a more stable configuration. No, that is not the case. Okay, so that should be remembered always. It is an important point. Now, eclipse and staggered conformation can be represented by Sauthe and Newman. So here comes the projections that will help you to kind of easily differ between the, means make a difference between the eclipse and staggered. So those are Sauthe and Newman projection. So let us see Sauthe and Newman projection now. So first we'll talk about Sauthe projection. So what is Sauthe projection? So in the Sauthe projection, what we do, the molecule is viewed along the molecular axis. Okay, where it is viewed along the molecular axis. So this is the molecular axis. So what is here you can see that if you are viewing from this side, from left hand side, and you are viewing along this bond, there is a bond, right? there is a bond like this. Okay, so if you're viewing from here, not from here, if you're viewing from here, then you're viewing along the molecular axis. Okay, and if you just project this on the paper, on the drawing the central carbon-carbon atom as somewhat longer straight line, the upper end of the line is slightly tilted towards the left or right hand side. The front carbon is shown at the lower end of the line, whereas the rear carbon is shown at the upper end. So we'll understand, try to understand it with the help of the diagram. And each carbon has 3 lines attached to corresponding 3 hydrogen atoms. Then the lines are inclined at 120 degrees. So this is your Sawhorse projection. Okay. So what it is being said here is that what you will do, you will see the molecule along the molecular axis, right? You will see the molecule along the molecular axis and try to project it on a paper. Now second is Newman projection. So in this projection, the carbon near the eye is represented as a point and 3 hydrogens are attached to the front carbon. Similarly, 3 hydrogens are drawn at angle of 120 degree to each other. The rear carbon atom, which is the back one carbon, is represented by a circle. The 3 hydrogen atoms are then attached to it by the shorter lines drawn at angle 120 to each other. So this is the diagram. So now you will get a proper idea. So what is it tilting and all? So see, this carbon here is tilted down, this carbon is tilted up to make a difference between this carbon and this carbon. So this is Sawhorse projection basically. Now these are the substituents that are attached to the carbon, 3 hydrogens. Similarly, in case of this 3 hydrogens, this is ethane. And if you look here, then this bond is in front of this bond. It is completely dominating it, or it is trying to hide the bond that is present on the back side. If you look here, if you look from along here. Similarly, this is eclipsing this carbon hydrogen. This carbon hydrogen bond is eclipsing this carbon hydrogen. So this is called as eclipse structure. Okay, this is called as eclipse structure, and it is with the help of Sawhorse projection. Okay. Now the second one is staggered. What is staggered? So in staggered, each of these are present opposite to each other, right? So the angle between this means it is rotated by an angle of 60 degree. Okay. So what you do, if you simply rotate it by 60 degree, each of the carbon hydrogen bond, then that would result in the backward this configuration, which is the staggered configuration. Okay. One more configuration I just want to put it here is the DLN configuration. You will study more about it, but just view of it is given here. So if your OH group, okay, if you're talking about the DL configuration, just keep this in mind. When you will need this, you will say that, okay, yeah, I have heard it. Okay, so just keep this in mind, that if the OH group on the second carbon, okay, so if you just arrange your given molecule from the highest oxidation state to the lowest oxidation state, so this carbon is on the most oxidized form, this carbon is the lowest oxidized form. Similar goes for this and this. Now if you arrange this in such a way, then the second carbon, okay, this carbon will be noted, and if the OH on this carbon is present on the right hand side, then we call it as D-glucose. If it is present on the left hand side, we call it as L-glucose. Now there are chances that instead of OH, NH2 can also be present. So we have like alpha amino acid, okay, D amino acid and L amino acids. Okay, we can have the case of that also. Next is Newman projection. So this is the eclipsed one and this is the staggered one. Now in the eclipsed one, although it is shown by a certain angle, but it is not so. It is completely hiding this, but to make things visible, it is given in this way. Okay, so you can see that there is a 0 degree angle. This is called dihedral angle. So this angle that I am talking about, so between this and this hydrogen, in this case it is 0 degree. In this case, this angle is 60 degree. Okay, this is called torsional angle or dihedral angle. So this is eclipsed one and this is staggered one. Clear? Now next is anti or staggered. Sorry, next is skew or gauche. Okay, so this is called skew and gauche, right? It's called skew or gauche. This is called fully eclipsed. All hydrogen are eclipsed. Fluorine and hydroxyl group are eclipsed. This is called eclipsed. Okay, this is also called eclipsed. This is called anti or staggered. Clear? So this is very important. These two projections are very, very important from your exam point of view. Questions are asked from here, from the projection part only, and it will help you to draw the mechanism also in the later on classes when you will study more about organic chemistry. Then you will find an application of this projections. Okay, you will find the application of this projections. Next, we will talk about the relative stability of configuration. So we have seen what are configuration, what are the possible configuration that can be available. Now we'll talk about their energy. So I have told you in the earlier form only that there is a relative change in the energy due to the change in conformation. Let us see that. So first of all, in a staggered form of ethane, the electron clouds of carbon-hydrogen bond are far apart. So we have shown torsional strain. Okay, this is basically the repulsion between the bonds. Okay, clear. Now staggered form of ethane, the electron clouds of carbon-hydrogen bond are as far apart as possible. Now, thus there are minimum repulsive forces, minimum energy, and maximum stability of the molecule. So in the staggered case, since when you have the eclipse case, if you just go and look back, then you can see that this bond here, this bond is just present in front of this bond. Now there will be maximum electron repulsion because the distance is very less. So there will be maximum torsional strain due to the bond-bond pair repulsion. Where here in this case, if you see that there is some angle between these. This is called a dihedral angle, and it is quite away from the bond. Okay, this bond is away from the bond. This bond as compared to eclipse structure, and that is the reason they suffer less torsional strain. Okay, and hence it stabilizes the compound. Next is, thus it may be converted that rotation around CC bond in ethane is not completely free. Now due to it's from here, since we have an energy barrier. Okay, there is an energy barrier because it is higher energy. So if you have to go on either side, then there is a energy barrier, and therefore the rotation of ethane is not free, means it cannot be rotated independently, and the energy difference between two extreme forms is of the order 12.5 kilojoule per mole. So this is the two extreme forms of the order of the 12.5 kilojoule mole. Okay, this is the energy difference between the two extremes. Okay, so between the eclipse and staggered, the energy difference is 12.5 kilojoule per mole. Now this is very small. Even at ordinary temperature, the ethane molecules get enough energy, enough kinetic or thermal energy, which is sufficient enough to overcome this energy barrier. Okay, so this is the thing that has been mentioned here, is that because the energy difference, the energy difference between the eclipse and staggered state is very less, due to which it can easily rotate and move up to another molecule. So this is the thing. Now this thus it can be said that rotation about carbon-carbon single bond in ethane is almost free for all or practical purposes. It has not been possible to separate and isolate conformational isomer of ethane. So since this energy barrier rotation is very small, so the energy which is required to rotate the molecule, it is called as barrier rotation. So since this energy is very small, okay, this difference is very small, so it is very difficult to isolate the conformation. So as soon as we isolate it, it can rotate, okay, due to even small amount of energy. So this is the energy versus rotation. So what are we doing here? So if you look here, so this is the eclipse form. Okay, this is the eclipse form. We started to rotate this. Okay, so what are we doing? We are rotating it. Suppose we are rotating the back carbon. So the back carbon by one rotation, each rotation is by 60 degrees. So 60, 120, 180, 240. So we're adding 60 degrees each time. So once we rotate it, this back electron comes here in between, because the angle between these two of the front carbon, these two is 120 degrees. And if we rotate by 60 degrees, this will go in the middle part. Okay, clear? Next. So as it goes there is minimum repulsion. We know that the torsional strain has been removed, and there was no steric strain before. Therefore, it will result in a very better situation. Okay, means it's a stabilized situation. Now again we rotated it because the energy barrier. This is called the energy barrier, by which the energy should be required to convert this to this, and this is approximately 3 kilojoule per mole, and it was being provided. Okay, it is being provided by the sun. Okay, so not the sun, being provided thermal energy that is being present in the atmosphere. Again we started to rotate by 60 degree. Again the energy will go down. So in this way we can rotate and get the infinite number of conformations, because in between these two, there are infinite points that are present here, and each of this point will represent one conformation. Okay, clear? So we have started from 0 degree and we have again rotated and came back to 360 degrees here. Now let us talk about the difference in conformations and configuration. So if I talk about the conformation, so it is just the three-dimensional arrangement in space of the atoms in a molecule which are interconvertible by rotation. Okay, so what we have done right now is we have just converted it. Okay, we have just converted it by simple rotation. Okay, we have just converted it by simple rotation, right? We don't need to break any bond or something like that. It is converted by simple rotation, and this interconversion does not require any bond breaking and bond making, and that is the reason we are acquiring such a low amount of energy. Okay, clear? Next is configuration. Now if I talk about configuration, to change a configuration means if you want to change from one configuration to another, then you have to break the bond. Okay, you have to break the bond, because it is not possible to convert two configurations just by rotation, and their interconversion is possibly only through breaking and making a bond. Clear? Okay, so this was all for today's class. With this I end my lecture. Thank you.